Hi all, today we're going to talk about perturbation theory, and this lecture is going to be a rather formal introduction to, or mathematical introduction to perturbation theory. In a later lecture we'll do more like an overview of the consequences with some examples and so on. But in this one I really want to lay the mathematical foundation for perturbation theory. So the idea here is that you have a Hamiltonian that you know the solution to, and then there is additional little change to that Hamiltonian. So you've got a unperturbed Hamiltonian H naught with solutions psi n 0 and En, so solutions where these are the eigenstates and these are the eigenenergies. So you know this one, and now what we're going to do is going to add a little perturbation. That perturbation could be an additional potential, like an electric field coming in, not too strong, relativistic effects that you haven't included in the original solution, an additional coupling, the additional particles, whatever it is. So something where it's a small change compared to H naught, and that way you can break it down into a kind of a layer by layer expansion. So the perturbed Hamiltonian is going to be written as follows. So you've got the original Hamiltonian, which is the unperturbed, and you add a small perturbation V to it. The lambda here is a small parameter. And we're going to keep that one here just so that we can keep track of it's going to become a measure of the smallness. But of course, sometimes the lambda will be absorbed into the perturbation V itself. And we'll see examples of all of that as we go. So if you want to go ahead and actually have a look at the examples first and then come back to this formal video, that's quite reasonable. Okay, and so the question is, how are the solutions changed? So the solutions are En, which is going to be close to the unperturbed one, because it's small, and exact solution psi n is going to be close to psi n naught because, again, lambda is small. How these solutions changed by the perturbation. So what we're going to end up doing is we're going to do an order by order expansion in the small parameter lambda. So we write the order by order expansion is going to be En equals En naught plus some small En1 plus a very small En2 plus dot dot dot. And that's also going to be written sometimes as En naught plus delta En1 plus delta En2 and plus dot dot dot. So that's the energies, and similarly the wave function will be expanded into the original wave function of the unperturbed Hamiltonian plus a small change, which is due to the perturbation. And we sometimes would write that as this. So the superscript 0, 1, 2 tells us the order of the expansion, and the subscript n is just indexing which state we're talking about. So n equals 0 would be the ground state, n equals 1 is the first excited state, and so on. Now, we want to get expressions for en1, en2, and so on, and we want expressions for psi n1, psi n2, and so on. Okay, so how are we going to get there? So firstly, we write h psi n equals en psi n, and I got to give this an equation 1. So now we take this and now multiply it by the bra psi n 0 and integrate. And so we get sine 0 h psi n is equal to en psi n 0 psi n. So now what I want to do is I want to actually expand the left-hand side a little bit more. So expand the left-hand side as psi n 0 h naught plus lambda v psi n, and now I want to apply the h naught to the left. That will give me en 0 psi n 0. So that's applied to the left, and that's the first term. And the second term is, I'll just take the lambda outside, and then I get psi n naught v psi n. And so if I take this as the left-hand side, so I'm basically get en minus en naught. So I'm subtracting the first term there, basically from here and from here, right? So it's the left-hand side. So I'm taking this first term here to the left-hand side and then keeping this one on the right-hand side. And I get lambda psi n 0 v psi n over psi n 0 psi n. And this is equation 2 that I'm going to need later. So this gives me so this equation is exact. Okay, I have not made any approximations so far. So now I have to start doing my order by order expansion. So the first thing I want to do is I want to set psi n is approximately equal to psi n 0 on the right hand side to obtain first order that's first order in lambda correction to the energy. So that'll be En1 is equal to, or I should say lambda En1 to keep the notation consistent equals lambda times psi n 0 v psi n 0 over psi n0, which is 1. I'll put that in. And so that's equal to lambda VNN. So VNN is just notation for the matrix element psi n0 v psi n0, and the denominator here psi n0 is 1 because we assume that the psi n0 is normalized. And so this gives us our first order correction to the energy. Next thing we want to do is get the first order correction to the wave function. So we will take our equation 1 before. So we take equation 1 again. Have a look at equation 1. It's this one at the top here, and you can see that it's just h psi equals e psi. So it's the exact equation, Schrödinger equation for the exact solution. But now we want to multiply not by psi n0, but by a different one, psi m0, where m is not equal to n, and integrate. So we will have h psi n equals e n psi n. That was equation 1. Now we're going to multiply it on the left by psi m0, but I'm going to just switch them around as well, because for the same reason I had to do it last time. Well, I didn't do it last time, but I probably should have. So I'll have e n psi m0 psi n. So that's the right hand side. We're just swapping the right hand side and the left hand side here. That's got to be equal to psi m0 h psi n, which is equal to, and now I do the same kind of expansion I did last time. This is going to be a little bit more difficult than the last step, but bear with us, it's not so difficult. Make the same expansion that I did last time. And once again, we get an exact equation where I have not made any approximations yet, and but it's not particularly useful. So we're going to have to go from this, and we'll make a order by order expansion, just like we did last time. And so I'll do the same thing I did last time. I take this wave function. It looks now like this. And the denominator is actually En minus Em0. So you can see how I've gotten that. I've just taken the first term on the right hand side to the left hand side. I've kept the psi m0 psi n on the left hand side, and I've divided through by the En minus En0. So now we want to do our order by order expansion. So this is exact. Remember, this is exact. So now we're going to do our first order corrections to lambda. And so we're going to use our expansion that we did as before. On the right hand side here, we can substitute psi n 0, e n 0, and keep it to first order in lambda, because there's this lambda outside already. This lambda is already outside. So to keep this right hand side to first order in lambda, there can be no lambdas inside here. And so we just need to take the lowest order, the 0th order for those. And so that gives us to first order in lambda. Right, and we can write that as we did before as lambda Vmn over En naught minus Em naught. Okay, so what does this mean actually? Because on the left hand side we've just got a number, which is the overlap of this psi n 0 with our exact wave function psi n, and this is our first order in lambda expansion of that term. So what does it mean? Well, to understand what we're looking at on the left hand side here, we need to do a little bit of work. What does it mean? So we express psi n as a linear combination of the complete basis psi m 0. Right? So in other words, we would say that psi n can be expressed as a sum over all m's of Cm psi m 0. That's not saying anything. It's just saying that the basis psi m 0 forms a complete set, which we know from linear algebra theory. So we know that all of the eigenfunctions of the Hamiltonian H0 will form a complete set. We can form any wave function from those functions. So given that we know that, we can then expand this out. We're going to have the first term, which is going to be something close to 1, because psi n is close to psi n naught. How do I know that? Cn is close to 1. How do I know that? It's because lambda is small, so it's a small perturbation. If it's a small perturbation, then psi n has to be close to psi n 0. It can't have changed too much. If it changes by a lot, it's not in the realm of perturbation theory anymore. The second part is all of the terms where m is not equal to n, and that's the ones that we were talking about just a moment ago, when we said, hey, let's multiply this by psi m 0, the bra, and integrate, right? So that's what we did up here. Yeah, take psi m 0 with m not equal to m and integrate. So we know that m is not equal to n is the expansion that we were looking for when we looked at equation at the top of your screen there. So given that, we can now start to express something like this. Psi m, or I'm going to get my letters all mixed up. How about I put a P in here? MNOP, but O's are too confusing. Psi n equals Cn psi p 0 psi n 0 plus sum m not equal to n of Cm psi p 0 psi m 0. Right? And obviously I want p not equal to n, so that's another thing here. So I want p not equal to n as well, and so this thing here is going to be 0, and this part here is going to be delta mp, right? So it's only non-zero when p equals m, and that will give us that psi p naught psi n is equal to Cp, p not equal to n. Okay, so now if we compare this equation with the equation at the top, so we get, again, we're comparing this equation that we just made with this one here, which is almost exactly the same, except there's been a change of lettering from M to P. But that's just an index, so don't get confused. So now we compare our equations. I'll give that one a number as well. Go back to M instead of P, and it was a first order expansion. So this gives us the first order expansion of the wave function. So when we're saying, how does this wave function change? You know, we've got this wave function, you've added this perturbation theory. We express that change in terms of all of the basis functions, psi m, or psi m0. And then all we need is the coefficients of that expansion, the Cm1. And so those will inform, or they tell us, how the wave function changes. So that's good for the m not equal to n. What about Cn1? What do I do about this one? So if we go back to psi n is equal to Cn psi n 0 plus, now we can say this, sum over m not equal to n of Cm psi m 0. And we know, and now I definitely need to change colors, we know that this guy here is order lambda because we've just written it one line above. And now I want to normalize it. So take a norm, and we'll do psi n is equal to, on the right hand side, the psi n zeros and the psi m zeros are all orthonormal. So they're all orthogonal to each other unless m equals n. So I can just take each term separately, knowing that all the off-diagonal elements are going to disappear. Cm squared. So I can say 1 is equal to Cn squared plus terms of order lambda squared, right? So all the Cm squareds have to be of order lambda squared. And so therefore, Cn is of order 1 plus terms of order lambda squared. And so we see that there is no first order correction to wave function from right. So in other words, Cn Cn1 equals 0. So putting all that together, we have lambda psi n1, or let me write that as delta psi 1 as well. You see it both ways, is equal to lambda sum m not equal to n vmn over en naught minus em naught psi m naught. And so that is the first order correction to the wave function. Great. And now we can easily find the second order correction to the energy. So to do that, you just need to take equation 2, which I'll go back and show you in a second, and you substitute in our first order corrected wave function. So let's just go back to equation 2 and have a look what I'm talking about. There's my equation 2, there's equation 3. Equation 2 is this one. And equation 2, it's an exact formula. But now on the right hand side, we've got the lambda out the front, and we're going to keep terms with lambda inside here as well. And so that will give us terms up to lambda squared on the left hand side. So that's the point of doing an order by order expansion. So let's do it. We've got substitute psi n equals psi n naught plus lambda psi n 1. And we're going to keeping terms of order lambda squared. So let's do it. So we got En minus En naught is equal to lambda psi n, and this one's a bit messy, but just bear with me. But psi n naught plus lambda psi n 1. So this is the approximation we're making, but the equation 2 is exact, but now we've only taken an expansion up to keeping terms up to second order in lambda. And it's that over, I must always be careful, psi n 0 psi n naught plus lambda psi n 1. Okay. En minus En naught on the left-hand side, we're going to expand that out, and so that just leaves us with the first order and second order corrections. So let's write that. Lambda En1 plus lambda squared En2 is equal to lambda, the first term here is Vnn, and the second term here is lambda squared. Oh, okay. Let's be careful here. Psi n 0 v lambda psi n 1. And the denominator has actually disappeared because our normalization at the bottom here, I forgot to put it in green like I did last time. The normalization of psi n is correct. It's 1 up to order lambda squared, as we showed earlier. So in other words, we don't need to introduce an extra lambda squared at the denominator, because then the whole thing would be order lambda cubed. So in fact, that denominator is important, but only at third order in energy or second order in wave function. So we don't need to worry about that. We won't go that far in this course. So this first term here is this one is of order lambda, and so that's En1, and this second term here is order lambda 2 or lambda squared, so that's going to give us En2. First thing is going to give us En1, as we saw before. So let's write out En2 is going to be equal to sum m not equal to n. Right, so now I'm expanding out psi n1. It's Vmn over En naught minus Em naught psi n naught v psi m naught, or Vmn squared over En naught minus Em naught. And so that's the second order correction to the energy. And that's probably a good place to stop. You can just keep going order by order expansion, right? So if you just have a look at our equations, our exact equations here, which are equations 1, standard one, equations 2, which is exact, and equation 3, which is also exact. Where is that? Here. So, wait, equation 3 is exact? No. This one's exact. Equation 3 is first order in lambda. So, but equations 1 and 2 are exact, and you can just do an order by order expansion, and then you can get your higher order, third order, fourth order, etc. But this is a good place to stop for us, because usually in practice you only ever need to go up to second order in the energy or first order corrections in the wave functions. And there are times where you need to go to higher order, but I've been working in atomic physics for 20 odd years, and I've pretty much almost never had to go beyond second order perturbation theory in that context. Okay, but of course there are contexts where you do need to go to higher order, and there is a clear mechanism for how to do that. So we'll stop there, and our next video will talk about the examples and some consequences, and we'll also introduce the Feynman notation. So hang around for that one. Bye.